So in this continuation now, we graphed the inverse relationship where the original function, original relation y equals 6 minus 2x is represented by this line here. And then the inverse relation is x equals 6 minus 2y. It's this line here. So we simply use the ordered pairs to graph these lines. And we can see that these lines are symmetric about the line y equals x. The next exercise is very similar. Find an equation of the inverse relation, then complete the table and graph both the original relation and its inverse. So the original relation is y equals x squared minus 4x plus 7. So then the inverse is equal to x equals y squared minus 4y plus 7. So here we have the ordered pairs for the original relation 0, 7, 1, 4, 2, 3, 3, 4, and 4, 7. And now for the inverse, when we calculate for y equals 0, then we have x equals 7. And when y is equal to 1, then x is equal to 4. And when y is equal to 2, then x is equal to 3. And when y is equal to 3, then x is equal to 4. And when y is equal to 4, then x is equal to 7. So these are the ordered pairs for the inverse relation. Now let's mark those points on the graph and connect them with a smooth curve. So here we have plotted the ordered pairs and connected them with a smooth line. And so here's the original relation, the graph of the original relation, y equals x squared minus 4x plus 7. And here's the graph of the inverse relation, x equals y squared minus 4y plus 7. And again, we notice that these graphs are symmetric about the line y equals x. Next, we look at the connection between inverses and one-to-one functions. And so here's the definition: one-to-one functions and inverses. A function f is one-to-one if different inputs have different outputs. That is, if a is not equal to b, then f of a is not equal to f of b. Or another way of saying that a function f is one-to-one if when the outputs are the same, then the inputs are the same. That is, if f of a equals f of b, then a equals b. And here's the next part. If a function is one-to-one, then its inverse is a function. From looking at the previous example, in fact, let me just bring that up again. You can see that with the vertical line test, that the original relation is a function. A vertical line test intersects the function at most once. But the inverse does not pass the vertical line test. So the inverse in this case is not a function. A vertical line will, or can intersect the graph in more than one point. So here's an example where the inverse is not a function. So again, if a function is one-to-one, then its inverse is a function. So we're familiar with the vertical line test, and now here's the horizontal line test. If it is possible for a horizontal line to intersect the graph of a function more than once, then the function is not one-to-one, and therefore its inverse is not a function. So when you look at these two graphs, here's the graph of f of x equals 2 to the x, or y equals 2 to the x. In the horizontal line test, the line will intersect at most once. And when you look at the inverse, x equals 2 to the y, again, a horizontal line test intersects the graph at most once. So in other words, here the inverse is also a function. The takeaway is that the inverse of a function may or may not be a function. The next few exercises are about determining whether the function is one-to-one and therefore has an inverse that is also a function. So f of x equals 4 minus x, and here's a graph of f of x equals 4 minus x, and it passes the horizontal line test, so therefore it has an inverse, and that inverse is also a function. So in other words, yes. So the horizontal line test tells us that the function has an inverse, and here's what the inverse looks like. X equals 4 minus y. In the next exercise, we have f of x equals x squared minus 1. And the horizontal line test shows us that the graph can be intersected more than once by horizontal line test. So the inverse, this is not a one-to-one function, and therefore it does not have an inverse. Now the graph of 4 to the x, we've graphed it before. It looks as follows. For exercise 9, I graphed the function, and it looks like this, and certainly passes the horizontal line test. In other words, it's a one-to-one function, and it has an inverse, and the inverse looks like this. X equals 4 to the y. And so in other words, the answer is yes. And the last example is f of x equals absolute value of x minus 3. So we're going to graph that and then find out if it has an inverse. When we look at the graph of f of x equals absolute value of x minus 3, it looks like this, and clearly it does not pass the horizontal line test, so it is not one-to-one, and it does not have an inverse. Part D is about inverse formulas and graphs. If the inverse of a function f is also a function, then it's named f inverse. Read f inverse. Here's a warning. The minus 1 in f inverse is not an exponent, and f inverse does not represent a reciprocal. So you've got to be careful what f inverse means and what it doesn't mean. So here are the steps for finding the inverse of a function. If a function f is one-to-one, the formula for its inverse, f inverse, can be found as follows. Replace f of x with y, interchange x and y, this gives the inverse relation, and then solves the equation for y, and then replace y with f inverse of x. Let's do some examples. Here are some exercises. Given each function, determine whether it is one-to-one. If it is one-to-one, find a formula for the inverse and then graph the inverse function if it exists. So for exercise number 11, f of x equals 3 minus x. So to find the inverse, we replace f of x with y. So y equals 3 minus x. Now we exchange x and y. So x equals 3 minus y. And we solve this formula for y. So y is equal to 3 minus x. So that's the inverse. F inverse of x is equal to 3 minus x. In other words, it's the same graph as f of x. So that's f inverse of x equals 3 minus x. It's the same graph. in this particular case. In the following example, g of x equals 3x minus 2. And so we look at the graph of 3x minus 2. And it passes the horizontal line test. So let's find the formula for the inverse. So step 1 is replace g of x with y. So y equals 3x minus 2. Now we exchange x and y. So x equals 3y minus 2. And when we solve this formula, this equation for y, then y equals x plus 2 divided by 3. In other words, g inverse of x equals x plus 2 divided by 3. So here we went through the steps to find the formula for the inverse. G inverse of x equals x plus 2 divided by 3. And here's the graph of the inverse. G inverse of x equals x plus 2 divided by 3. And that is symmetric to the original the original function. One-to-one function. It's symmetric about the line y equals x. So now we can state a generalization that the graph of f inverse is a reflection of the graph of f across the line y equals x. And so the next exercise asks us to graph g of x equals 3x minus 2 and its inverse, g inverse of x equals x plus 2 divided by 3 using the same set of axes. Here you have the graph of the original function g of x, 3x minus 2. And here's the graph of the inverse, g inverse of x equals x plus 2 divided by 3. And here's the line y equals x, and you can see that the f inverse, or g inverse rather, is a reflection of g of x across the line y equals x. For the next exercise, we are given that f of x equals x to the third plus 1. And so part A is determine whether the function is one-to-one. So I graph the function, and here's f of x equals x to the third plus 1. And it passes the horizontal line test. So in other words, it's a one-to-one function. So the next step is to find its inverse. To find the formula for its inverse, we replace f of x with y, so it gives us y equals x to the third plus 1. Now we exchange x and y, so x equals y to the third plus 1. We're solving this formula now for y, so y to the third equals x minus 1, and then y equals the third root of x minus 1. So then f inverse of x is equal to the third root of x minus 1. Now we want to graph this function, f inverse of x equals third root of x minus 1. And here we have the graphs of f of x equals x to the third plus 1, and its inverse, f inverse of x equals the third root of x minus 1. And again, we notice it is symmetric across the line y equals x. Here's the inverse, and here's the original function, and they're symmetric across this line y equals x. Here's the connection between inverse functions and composition. Suppose we use some input x for the function f and found its output f of x. The function f inverse would then take that output back to x. Similarly, if we began with an input x for the function f inverse of x and found its output f inverse of x, then f inverse of x, then the original function f would take the output back to x. So here's the summary of that. If a function f is 1-to-1, then f inverse is a unique function for which the composition of f inverse and f of x equals x, and the composition of f and f inverse of x equals x also. So let's investigate this in one example here. When we have the function f of x equals 2/3 x minus 4, and use composition to show that f inverse of x equals 3x plus 12 divided by 2. Let's begin with the composition of f inverse and f of x. So that means this is f inverse of 2/3 x minus 4. So that would be 3 times 2/3 x minus 4 plus 12 divided by 2. So what we're doing here is we're replacing x with 2/3 x minus 4. So then in the numerator, we have 3 times 2/3, so it'd be 2x. And 3 times minus 4 is minus 12, plus 12 divided by 2. So then the 12s cancel, and we have 2x divided by 2, so that's equal to x, which is what we wanted to prove. When we take the composition of f and f inverse of x, that means f of 3x plus 12 divided by 2. So now we replace x in this expression for f of x with 3x plus 12 divided by 2. So that means we have 2/3 times 3x plus 12 divided by 2 minus 4. So that's equal to 2 times 3x is 6x, and 2 times 12 is 24, divided by 3 times 2 in the denominator, or 6, minus 4. And so now in the fraction, we can factor out a 6 in the numerator and cancel against the 6 in the denominator. So we have 6, we have x plus 4 minus 4, and that's equal to x. So in both cases, we've shown that f inverse is equal to this expression, 3x plus 12 divided by 2. Because we took the composition of f inverse and f of x, and we took the composition of f inverse. In both cases, the result was x. That proves it. And this is the end of section 8.2.